everyone. You are watching the 18th lecture in the series Mathematical Methods for Economics. The lecture today is in continuation to the discussion that we had in the previous lecture, which is lecture 17 on limits. In this video also, we will continue with our discussion on limits. In particular, we will go over some practice problems. In fact, if you have watched the previous lecture, in the last lecture, we had developed some basic rules for calculating limits, the general rules as well, and some theorems as well. So, when we go over these problems that we'll do today, what you should do is you should note how these rules for computing limits are to be applied and when they are to be applied. So you should know which rule to pick out when from your toolkit when you're calculating limits. However, before I bring in the practice problems, the focus of the discussion today actually will be some exceptions to the rules for computing limits. We'll be talking some exceptions to the rules, the exceptions rather than the rule that you must be alert about while calculating limits. Let us first do a quick recap actually of the first part that we had done in the previous lecture. We'll do a quick recap before we go over the exceptions to the rules and we'll go over the main concepts that we had developed in the previous lecture. We'll also quickly summarize the rules for computing limits because that will be the basis for today's discussion. Okay, now as I pointed out earlier, limits are the fundamental building block for studying rates of change, for studying calculus in a larger sense. So if you've done derivatives, you would know that you first start with the concept of a limit and you use the limit to calculate a derivative. So what exactly do we mean by this concept? The concept of a limit is concerned with the idea of approaching or coming close to a particular value without necessarily having to attain that value. So I could talk of a variable coming close to a particular value, coming sufficiently close to a particular value without necessarily attaining that value. Or I could think of the corresponding function of that variable coming sufficiently close to a particular value without necessarily attaining that value. So these are the concepts that we will be developing. Now, if you've noticed, the way I've phrased this concept is, I'm saying variable or the function, these come sufficiently close to a particular value. Now, this phrase that we have here, sufficiently close, coming sufficiently close to something, that actually can be given a very nice mathematical interpretation, which will then take us to the precise mathematical definition of the limit, which we'll actually cover in a later lecture. But for now, let us look at the preliminary definition of the limit that we had developed in the previous lecture. I'll just go over it. This is, in fact, the preliminary definition of the two-sided limit. Now, what we are talking about here is, let's suppose we have a function f, which is defined for all values of x near the point a. So the function may or may not be defined at x equal to a, that does not matter. It is defined for all values of x near a. The question that we are going to ask is that if the variable x, if the independent variable here x, comes sufficiently close to a, then what is a value that the function f of x comes sufficiently close to? Okay. In other words, what is the value that f approaches, or what is the limiting value of f? So see how I'm using the word limit, how I'm bringing in the word limit. It's a limiting value. F is coming sufficiently close to a particular value, so that is the limiting value. So let's suppose that as x comes sufficiently close to a, f of x tends to a particular value L, which is a finite number here, because for a limit to exist, you have to have a finite number. And that we then write as the limit of the function f of x as x tends to a, that is equal to the limit L, the number L. Okay, so this is what we call the limiting value. What we are saying here is that the function approaches L as x tends to a. Now, as I just mentioned a little while ago, that the function may or may not be defined at a, but that does not matter. We are not interested in the behavior of the function at x equal to a. We are interested in the behavior of the function around x equal to a. So we want to look at what happens to the function as x approaches a from values less than a, and what happens to the function as x approaches a from values of x more than a. And this then is a concept of the two-sided limit. We have to look at how what happens to the function as x approaches a from both sides. And this is as against the concept of a one-sided limit, where we either look at x, what happens to the function as x approaches a, either from values less than a, which then gives us the left side limit, or we look at what happens to the function as x approaches a from values to the right of a, which then gives us the right side limit. Now, as far as the two-sided limit is concerned, we have to set up both the left side limit and the right side limit. Both have to exist and both have to be equal to each other. In fact, this particular set of conditions then leads us to what are the necessary and sufficient conditions for the limit to exist. So these are important. This is actually a set of conditions. And these conditions are, first of all, the two one-sided limits of the function at the point A must exist. Okay, and the second condition is, so first is the existence part, that the two one-sided limits must exist. Both the left side limit and the right side limit must exist. And the second condition is that the left side limit should be equal to the right side limit. Both the left side limit and the right side limit should be equal. So let's look at the statement. So it's an if and only if statement, because these conditions that we've pointed out are both necessary and sufficient. So this statement says that the limit of the function f of x as x tends to a is L, if and only if the limit of the function as x tends to a from values less than a is equal to the, so that was the left side limit earlier, is equal to the limit of the function as x approaches a from values higher than a. Both the left side limit and the right side limit have to be equal and equal to L in this case. Okay, so these are both the necessary and the sufficient conditions, that first of all the limits have to, the one-sided limits have to exist, and both these limits should be equal to each other. Now note here, if now it is quite possible that one or both of the one-sided limits may fail to exist. So if that happens, that will totally violate this first condition itself. Okay, so if that happens, if either one of the one-sided limits or both of the one-sided limits fail to exist, then you can't talk of the limit, the existence of the two-sided limit in this case. Okay, both the one-sided limits of the function must exist, and the second condition also must be satisfied, that the two have to be equal. So yes, you may have both the one-sided limits existing, both the left side limit and the right side limit may exist, and they may both be finite numbers, but if they're not equal, then again we will fail this condition for the existence of the two-sided limit here. So these are conditions that you must be alert about, that these conditions, both of them are both necessary and sufficient. It's a set of conditions that must be satisfied. And this then actually, if you go back to the previous lecture, you can go over the various cases where the limit may not exist, the two-sided limit, because you could have a situation where, let's say, a function from one side is shooting off to infinity, or from both sides is shooting off to infinity, or from one side is shooting off to infinity, from the other is shooting off to minus infinity, or it may be that you have the left side limit and the right side limit existing, but they're not equal. So these are cases where the limit will not exist. Okay, now let's talk about the rules for computing limits, and these then, I'm just going to do a summary in this lecture because we'll be needing these rules to talk about the exceptions to the rules. But if you want to study these rules in detail, you can go back to lecture 17. Now, these two rules that I've put here, these are very elementary, very straightforward rules, very intuitive, but at the same time very powerful. In fact, on the basis of these two rules, you get a lot of results which you will see in a bit. So what does the first rule say? The first rule says that the limit of a constant c as x approaches a is equal to a constant. Basically, you can think of a function which is a constant c, right? So basically, regardless of the value that x takes, the function is just a flat line, and it's a flat line at the constant c, whatever that constant is. So basically what this is saying is that a constant is what a constant is. You can't change it. So if the limit of that function as x approaches a, whatever value x may approach, the constant is what the constant is. So that limit is going to be c at every point a. Now what does the second rule say? The second rule talks about the function f of x equal to x. Now this is a very simple function. It is this 45-degree straight line that passes through the origin. It makes a 45-degree angle with the x-axis. So what this is saying is that whatever the value of x is, the function will just echo that value, right? So the value of the function is exactly the same as the value of x. So when I take the limit of the function, limit f of x as x approaches a, that is because f of x is nothing but x, so that will be the limit of x as x approaches a, and because x takes on the same value as a here, so the limit itself will be a. Okay, so this is true for every point a, and these are the two elementary rules that I wanted to introduce immediately. We'll now go over some general rules for computing limits. Now, to understand these general rules, we'll just set up a bit of a base here. So let's suppose we have two functions, f and g, right? And again, these are functions which are defined in the neighborhood of a. They may or may not be defined at a, that's besides the point, but they are definitely defined in the neighborhood of a, which allows us then to investigate what the limit might be if it exists. Okay, and in particular, okay, so here the limits do exist. So we have this assumption that the limit of the function f as x tends to a is capital A, and the limit of the function g as x tends to a is capital B. Okay, so these are limits, these are the two-sided limits, and these you can see these are finite numbers, and the limits exist here. The first rule says that the limit of the sum of the two functions, so if I take f of x plus g of x as x tends to a, that is nothing but the sum of the individual limits. So that is nothing but the limit of f of x as x tends to a plus the limit of g of x as x tends to a. And because the first limit of f as x tends to a is capital A, and the limit of g as x tends to is capital B, so that gives us a plus b. Okay, and in words, this is simply saying that the limit of the sum is the sum of the limits. In fact, this rule can be generalized. Let me just move forward a little bit. It can also be generalized to n functions. So, for example, look at the screen here. If you have n functions, f1, f2 through fn, then the limit of the sum of these n functions, which is f1 plus f2 and so on till fn, as x tends to a, is nothing but the sum of the individual limits, which is limit of f sub 1 as x tends to a, plus the limit of limit of f sub 2 as x tends to a, and so on till the limit of f sub n as x tends to a. Let us look at the next rule, the second one. This is also quite straightforward. So this is simply saying that the limit of the difference f of x minus g of x, so the limit of the difference between two functions f of x and g of x as x tends to a is equal to the limit of the function f as x tends to a minus the limit of the function g as x tends to a, which is then a minus b. Okay, the third rule says that if I now consider the product of the two functions, limit of the product, so the limit of the product of two functions, f of x times g of x as x tends to a, is the limit, it is a product of the individual limits. So it is limit of f of x as x tends to a times limit of g of x as x tends to a. And that is then going to be a times b. And as we just showed for the case of the sum, even for the product, so the rule here is saying that the limit of a product is the product of the individual limits. This rule can also be generalized to n functions, and you can see here in the bullet point 2, I have taken the product of these n functions, f sub 1, f sub 2, and so on till f sub n, and the limit of this product as x tends to a is the product of the individual limits. You can see it's limit f sub 1 as x tends to a times limit f sub 2 as x tends to a, and so on till limit f sub n as x tends to a. The next rule is again an important rule. It is saying that the limit, if I take the ratio of two functions, okay, f of x divided by g of x as x, and I take the limit as x tends to a, then this is nothing but the limit of the function f as x tends to a divided by the limit of the function g as x tends to a, which will then be a by b, but it is this rule applies provided that the denominator, the denominator capital B here is not 0. So the limit of the function g as x tends to a, that should not be 0. As long as this is not 0, you can use this rule, which is saying that the limit of the ratio of two polynomial functions, polynomials, is equal to the ratio of the limits. And we also did this theorem in the previous lecture, where if the limit in the denominator, if you get a 0 in the limit, then we have two cases, because depending on whether the numerator tends to 0 or the numerator is something finite, you will get different results. So I'll show you that theorem as well. Okay, and the final rule is that the limit of the function f of x to the power p by q as x tends to a is, because the limit of the function f of x as x tends to a is capital A. So it's simply capital A to the power p by q, as long as capital A to the power p by q is defined. Right. Now, one more point I would like to make about these rules as far as these rules are concerned. One more extension is that these rules, because till now we were looking at the application of these rules as x tends to a, but note here that these rules also apply when x tends to a from the left, or x tends to a from the right, or x tends to infinity. So if you're taking limits at infinity, or so if x tends to infinity or x tends to minus infinity, then also these rules will apply, as long as the assumptions that we've laid out are true. Okay. Now, this is one of the theorems that we set up last time, and because this will be helpful for the problems that we do, I'll just talk about this as well. So this says that if we have any polynomial p of x, which is given by c0 plus c1 times x and so on till cn times x to the power n, and any real number a, so the limit of the polynomial as x tends to a is nothing but p of a. So that's going to be c0 plus c1 times a and so on plus cn times a to the power n. So that's just substitute x equal to a in the polynomial itself. Let's look at an example to illustrate the use of these rules. It's a very simple polynomial that you have here. You have a quadratic function, and you want to find the limit of px squared plus q times x plus r as x tends to a. Now, p, q, r here are constants. So this, because we know that the limit of the sum is the sum of the limits, so we can separate out these terms, and we can write this as the limit of p times x squared as x tends to a plus the limit of q times x as x tends to a plus the limit of the constant r as x tends to a. That is what you'll get in the second step. And then, because the limit of the product is the product of the limits, so you'll get limit of the constant p as x tends to a times limit x squared as x tends to a plus limit, again I'm separating out the q and the x and I'm taking the product of the two individual limits plus limit of r as x tends to a. Now, as I just told you, the rule 1 that we talked about earlier says that the limit of a constant is the constant itself. So, the limit of p as x tends to a is p itself. I have further broken up x squared into x times x. So, that becomes, when I take the limit, I get limit of x as x tends to a times the limit of x as x tends to a. Plus, again, when I apply the limit to a constant, I'm going to get a q here times the limit of x as x tends to a plus the constant r. And also, as when we did rule 2, that was saying that the limit of x as x tends to a is equal to a. So that then leads us to this result, that the limit of px squared plus qx plus r as x tends to a is p a squared. So these two limits will contribute an a each, and you'll get p times a squared plus qa plus r. Okay, and now we come to the interesting part of this lecture, which is asking, are there any exceptions to the rules that we have just talked about? And yes, there are some situations that you have to keep in mind. Now, if you go back to these rules that I just talked about, the general rules for computing limits, the assumption that we used was that the limit of the function f as x tends to a is this finite number capital A, and the limit of g of x as x tends to a is this number capital B. The question we're now going to pose is that, do the rules apply when both the functions f of x and g of x both tend to infinity? So instead of having these finite numbers a and b, do the rules apply when instead of the functions tending to a and b respectively, both the functions tend to infinity? And let me talk about some of these rules. So if both the functions f of x and g of x tend to infinity, we can say that the rules relating to the sum of the two functions and the product of the two functions will apply. The rule relating to the sum said that the limit of a sum is a sum of the limits. Now look here, if I want to calculate the limit of the sum of two functions f and g when both f and g are becoming infinitely large, then clearly the sum will also become infinitely large, right? So in that case, we say that the limit of f plus g is equal to infinity. Similarly, if I were to look at the product of f of x and g of x, as both functions tend to infinity, both functions become arbitrarily large as x tends to a. So the product will also become arbitrarily large, and therefore here also we get infinity. The problem arises when you're looking at the difference of two functions. So if I'm looking at the limit of f of x minus g of x as x tends to a, now I can't say anything, because what will happen is, because each one of these functions is tending to infinity, what will happen is the end result, what you'll get as the actual limit, or if it exists, that will depend on how fast the function f moves to infinity relative to the function g. So it is the relative rate at which both these functions shoot off to infinity that will determine what you will get as the difference when you're calculating the limit of the difference of two functions. Okay. And similarly, when we are talking of the ratio also, with the limit of the ratio of two functions, then here also we can't say, if both functions f and g tend to infinity as x tends to a, then the limit of the expression f by g, that will depend on how fast f and g move to infinity relative to each other.